Today on My Climate Journey's Startup Series, our guest is Stanley Janicki, Chief Revenue Officer at Sedron Technologies. Sedron is on a mission to revolutionize how waste streams can be processed to eliminate disposal costs and destroy pathogens, while capturing valuable energy and recycling water. Their Varcor system takes liquid waste slurries and recovers nutrients for beneficial reuse. Their primary go-to-market implementations today are in three areas: dairy and animal agriculture, wastewater treatment, and distillery waste. The company launched in 2014 as a spin-out of a business called Janicki Industries that was founded in the 1990s by Stanley's parents. Janicki Industries primarily focused on aerospace engineering, but in 2011, they were selected by the Bill and Melinda Gates Foundation to develop solutions for sanitation challenges in the developing world. They developed a product that created electricity and clean drinking water based on an input of human biosolids, aka poop, which they deployed in Senegal. They have a video of Bill Gates famously drinking clean poop water out of the system. The insights from these endeavors led to the creation of Sedron and the focus on converting liquid waste streams into organic fertilizers while reducing environmental runoff, transportation-based emissions, methane, and most critically, the use of fossil fuels to create nitrogen fertilizer. We mentioned Sedron briefly in an earlier episode we recorded with Bill Caesar at Generate Upcycle, as the two companies have an active partnership, which Stanley also touches on. And I'd like to thank former MCJ podcast guest Steve Simon for introducing us to Stanley. While it's tempting to make jokes about poop, honestly, I don't think I can help myself. Stanley helps shine a light on just how much chemical value there can be in it and in waste in general, and how harnessing it can move us away from a number of challenged environmental practices that have become mainstays of modern society. But before we start, I'm Cody Sims.
I'm Yin Lu.
And I'm Jason Jacobs. And welcome to My Climate Journey.
This show is a growing body of knowledge focused on climate change and potential solutions.
In this podcast, we traverse disciplines, industries, and opinions to better understand and make sense of the formidable problem of climate change and all the ways people like you and I can help. Stanley, welcome to the show.
Thank you for having me. Really appreciate it, Cody.
I get to be all sorts of sophomoric on this episode and talk about poop and pee, and we are going to have so much fun with that, I'm sure. But it's this incredibly serious problem that you all are solving. Maybe start out just with the highest level of what is Sedron?
Yes, Sedron is a very passionate group of people set out to transform waste. And when I say waste, I use quotation marks because it's not waste. It's something that is treated in a way that is wasteful. And we should capture that and do something productive with it. So we're a group of passionate, excited people who are set out to take that waste and transform it into productive, viable byproducts that displace the use of fossil fuel-derived products and remediate the deleterious impact of the original waste stream. So we're really excited about the concept of upcycling and how we can take those various products and produce wonderful byproducts with them.
There was a Forbes article from, I think, last year that had an incredible headline that you are closing the loop for poop. And I'm curious how, when you talk about waste, in particular, did, I guess for the lack of better terms, sanitary waste become the primary focus of your technologies?
No, sanitary waste is not the primary focus. It's one of many focuses.
Okay, well, good. Thanks for the correction.
Yeah, well, that's what's so incredible about waste is when people think of waste, they think of flushing their toilet, and that's a waste stream. But that's one of thousands of waste streams that go into the environment in some way. And saying, can we take all of those waste streams? And that's kind of a key point, again, of what Sedron is. They're very heterogeneous. Traditional technologies to process waste are almost always based on that specific waste stream. And yet with Sedron, the idea is, can we develop a technology that can process thousands of different types of waste streams, whether that's human waste, dairy waste, hog waste, stillage waste, distillery waste, fracking waste, you name the type of waste stream. And the system that we've developed is actually applicable to each of those.
And the specific technology that you all are really leaning into is called mechanical vapor recompression. Is that the thing that you all have really nailed down?
Yeah, so mechanical vapor recompression is a well-known old technology that's been used for decades in desalination plants, in propylene glycol recycling, which is de-icing fluid at airports. It's used in condensed milk factories. What we've done is we've combined it with a distillation process and thin film drying and a number of other processes to produce a dry product, a solution of low boiling point constituents such as alcohol or ammonia, and then to produce a very clean water. So our technology is mechanical vapor recompression is the core, but it's what we call the Varcor system. And Varcor is actually an acronym for vapor recompression and concentration and recovery. So it allows us to be able to recover and concentrate what we're doing through mechanical vapor recompression. And mechanical vapor recompression, you can really think of as a highly efficient form of distillation that's, again, well known.
And for the waste streams that you all are looking at, is it primarily focused on liquid streams? And for example, you guys were mentioned on the show we did with Generate Upcycle with Bill Caesar. They're doing all sorts of work in anaerobic digestion, taking solid waste of various forms, running it through these digesters and creating biogas and whatnot from it. Explain a little bit about how Sedron is doing something different in that regard.
Yeah, so we'll take liquid waste streams. It's very common that anaerobic digesters actually will produce a liquid product, the final product they produce. So we actually, in some of our installations, will take an anaerobically digested waste stream. In other situations, we'll take a pure liquid waste stream, such as hauled septage, which is pumped out of a septic tank, or stillage, which is the back of a distillery, a liquor distillery, or a fuel ethanol distillery. We also, in some cases, will take septage and we'll actually blend it with a cake product to make a liquid product. And it allows us to process it. So we'll take some solid products in cases. But generally, our technology is really around taking slurry waste streams and producing a dry product, very clean water, and a solution of those low boiling point constituents, such as ammonia.
And you mentioned today, one of the challenges is most of these different waste streams have different methodologies for dealing with them that are waste stream specific. What are some of the processes that waste goes through today, whether it's sewage waste, whether it's agricultural from cattle or hogs, as you mentioned, or some of these liquid waste streams coming off of an anaerobic digester? What does the world do with them currently with you not in the picture?
Yeah, exactly. I'm actually going to take it back. I'm going to take a step back on that question. It's a phenomenal question. So closing the loop for poop, what does that actually mean? Now let's take a step back. Today, right now, there are thousands of people that show up to work every day, and 3% of worldwide greenhouse gas emissions that take N2 molecules from the environment and turn them into NH3 molecules via the Haber-Bosch process. There's another group of people. And now what happens to that NH3 molecule? It gets put onto a plant. The plant gets eaten by a cow. You drink the milk from the cow, and eventually it ends up in your wastewater plant. Now, in that wastewater plant, there's a process known as nitrification, denitrification.
And just before you even go further, just for people to unpack, that means taking nitrogen waste stream from a cattle and turning it into ammonia that can go onto crops. Is that, just to put it into layman's terms, is that correct?
Yes. So actually, it's the Haber-Bosch process. It takes nitrogen molecules, N2 molecules, from the air, turns them into NH3 molecules. And that's ammonia, which is a plant-available fertilizer. You fertilize a plant, the cow eats the plant, you eat the cow, and then here you are with that in your body. You go to the bathroom, it ends up with the wastewater plant. If you take those NH3 molecules and you put them into a river, what ends up happening is you get these algae blooms, you get nutrient pollution, eutrophication. You destroy these water bodies. So wastewater treatment plants, what do? They run through a process known as nitrification, denitrification. And they take those NH3 molecules, the ammonia molecules, and then turn them into N2 molecules. That process takes 3% of worldwide greenhouse gas emissions right there. But what is that actually doing? It's undoing the work of the first 3% of worldwide greenhouse gas emissions. So the idea is we step in there with this technology and capture that ammonia at the wastewater plant or other places.
And most of the GHGs at these wastewater plant is coming from a combination of the energy used in the process as well as the off-gassing of various methane and nitrous oxide. Is that accurate?
You've nailed it. Very well done there. There's a wide range of places where the treatment process itself, the existing, quote, state of the art, has leakage of different things that are GHG, and of course, energy to run the process.
That's a wastewater facility that, I think most of us aren't quite familiar with, but we can understand what happens. You flush the toilet and run your dishwasher or whatever, and all of that stuff goes to one place and then has to be dealt with in order to turn it into clean water. And you end up with this sludge or slurry of stuff left over. What typically happens with that?
So that product right now in a wastewater plant, it can either be anaerobically digested and they can capture some natural gas from it, methane, or it doesn't have to be, not always. It will usually go through some sort of dewatering process. And then that sludge cake will be what's referred to as a biosolid, a Class B biosolid in that case. That will then be hauled to a field somewhere and applied. In the example of you down in you in Los Angeles, what happens? You flush the toilet, it goes to the plant, they haul it all the way to Arizona and put it on the fields. Here, I'm just north of Seattle right now, flush the toilet, it ends up almost in Idaho, is how far it's trucked.
And usually it's not put on food for human consumption, but it's put on food for animal consumption.
It cannot be, because it's a Class B biosolid. It still has pathogens, right? It still has vector attraction issues. And so what happens is it's going very far away, going on a subpar crop, and of course, tremendous trucking costs. Miami, there's products that are in South Florida that are sent all the way up to Georgia or Alabama because of that population density and the range that it has to go. Our system, what we do is we actually take that, what would be a Class B product with pathogens and other things. We go through our process. We extract the ammonia out, produce a concentrated plant-available ammonia fertilizer, produce clean water that can be used, for example, a project we're developing in Florida, it's going to be used to irrigate a golf course. And then, of course, that dry solid we produce is then referred to a Class A biosolid, such that it can be applied anywhere as a fertilizer. And because of its high caloric content, it's dry now, it can actually be used as a fuel for cement kilns or other such applications.
I do want to go into your solution. I want to set the context a little bit first, but I guess I have one question on what you just said. So the biosolid that comes out of your solution, even if it originated as human waste, is treated such that it is now a Class A biosolid and can be used for direct fertilization. Did I follow that correctly?
Yes, it's regulated then as a fertilizer.
And I'm torn on which direction to take the conversation, but let's keep going this route. What is it that is different about biosolids that are emerging from even an anaerobic digester that is a sewage cake?
We've heated our product up to 100 Celsius for an extended period of time. In doing that, we destroy all of the pathogens. Pathogens are completely destroyed. The other thing that we do is we produce a dry product. This product is dry. It's 90% dry. And by doing that, you can set it on the counter and it's just fine. Nothing would go to it. Imagine dry flour on the counter versus a cake or a pie. Imagine how long if you set them outside before something would be growing in the cake or the pie versus the dry flour. By being a dry product, it has what's called lower vector attraction. Flies and things are less likely to go onto it to produce more pathogens.
If I understand correctly, it is this actual cake that you're using as the fuel to generate the heat that actually makes the whole system operate. So there's sort of closed loop around the energy footprint of your system as well. Am I fully grokking that?
There's two main technologies that we've developed. One is the omniprocessor, which combusts the biosolids. And we built that in partnership with the Bill and Melinda Gates Foundation. The second technology is the Varcor system. The Varcor system produces this dry product. It's suitable for combustion, so we could combust it. Generally, we don't, because there's existing combustion infrastructure that can be used, such as cement kilns, or that's a very desirable product as a fertilizer. So in the dairy waste sector, that product's actually certified organic. And with the certified organic fertilizer, there's a tremendous desire for a pathogen-free, certified weed-free fertilizer.
So there is then some power cost to achieving the heats you need in order to do the pathogen removal.
Exactly. And that takes us back to mechanical vapor recompression. We can boil a gallon of water for 30 times less energy than conventional evaporative processes. So the energy input is actually very low relative to the amount of work we're getting done.
Explain that a little bit more for me.
So mechanical vapor recompression, the core piece of our technology. If you take a gallon of water or a pound of water, we heat that water up to saturation, so 100 Celsius. We evaporate that product. We then take that product and we run that vapor and we run it through a compressor and we increase the temperature and pressure of that vapor to say 110 Celsius. We now have a 10-degree delta between the incoming stream and the vapor we now have. We can then take that vapor and we can condense it back on the incoming stream. And it will give up its heat of vaporization and boil more water. And we get that back. So the only energy we had to put in was to heat the product up 10 degrees with the compression. That's the magic. That's a known process. But what we've done is we're able to take products from a slurry, like septage, biosolids, dairy manure, digestate, and go to a dry solid in a single step. That's very unique. And then, of course, capture the ammonia separately.
Let's take it back to the waste stream examples. So we talked through human waste streams and what tends to happen. Your initial go-to-market, for the most part, has been in the dairy industry, as I understand it. Sounds like technology is applicable to multiple potential use cases. But in the dairy industry, what are the challenges inherent therein in the existing waste stream processes?
Yeah, absolutely. Just really quickly, we're currently in 3 major industries. The first being dairy, as you mentioned, that was our initial foray. The second is the industrial municipal biosolid space. So we actually have an operational site in South Seattle running on human waste every day. And the third is actually on distillery waste. So we've done a project in the US Virgin Islands, and we're developing a project now in Kentucky to take distillery waste. We'll jump in now. What do dairies do today? What is the, quote, state of the art? There's been a tremendous consolidation of dairies to larger dairies that have more and more cows to produce more and more milk, obviously. What ends up happening is that they collect the dairy manure. Oftentimes, they'll go through an anaerobic digester. This is very common on the larger dairies. That's actually a bonus of the larger dairies, is that because you have economies of scale, you can actually apply technology such as an anaerobic digester that help with the greenhouse gas emissions. Goes to the anaerobic digester, they capture the gas. It then goes into what's referred to as a dairy lagoon. It's literally a ginormous pond. Tens of millions, potentially hundreds of millions of gallons of dairy manure are stored in one central concentrated location. From there, that manure has to get trucked or piped to fields and applied as a slurry. That's the state-of-the-art solution today.
In the lagoon, the goal is actually to have it broken down by bacteria and whatnot. Is that correct? What are the lagoons trying to achieve in the process?
The lagoons, especially Midwestern dairy lagoons, are really around time of application. If you're in Wisconsin and you're in January, you cannot apply dairy manure to the fields because the fields are frozen solid. It's really storage more so than anything else. That's the issue, is that there is biological breakdown in there. You get ammonia evaporation, volatilization out of that lagoon. You'll lose 70% of your ammonia when you store your product in a lagoon like that. That ammonia is not doing anything good when it evaporates into the atmosphere, right? It's going to make acid rain. It's going to come down. It's going to cause nutrient pollution. You're getting biological activity in that lagoon. Even if it's been anaerobically digested, there's still 30 to 40% of the methane that can still come out of that lagoon. Methane, again, is like 40 to 80 times as much of a greenhouse gas as CO2. So it's tremendously bad when that happens. So you're in an area where you have this lagoon. It's emitting nasty things. It's also kind of a ticking time bomb, because what happens if that lagoon were to leak, right? You'd have a real problem there with that. The other issue is that as a slurry, what goes into a lagoon is, say, 2 to 4% solids. It's 96 to 98% water. You can't truck that very far. It's prohibitively expensive to truck. So what ends up happening is it's very common that you get over application of nutrients near a dairy farm or other sort of large animal organization because they can't truck it as far. And so what happens is you get nutrient pollution. Whereas if you install a technology such as the Varcor, you now eliminate the manure lagoon and all of the deleterious environmental impacts from that. You get clean water that you can either irrigate with or feed to the cows. You end up with a dry, concentrated fertilizer. And now remember, that was 2% of the product before, so you have to do 98% less trucking. You can ship this 3 states away economically. And that's a wonderful fertilizer, again, organically certified. And then a nitrogen fertilizer, a liquid nitrogen fertilizer from the ammonia product. Again, easily shippable, precision applied, plant available. So from an environmental standpoint, we feel we have a large project under construction in Indiana right now. It's a 20,000 cow dairy. We'll be turning on after the new year. It will be the first, what we believe, and we're going to have data measurement, the first carbon neutral dairy in existence. Because think about the other things this allows you to do. If you don't have to apply liquid dairy manure, you don't have to till your fields anymore. You can go to no-till farming. No-till farming can allow you to sequester carbon into the soils. There's substantial research being done on this today on the efficacy of no-till farming. So if you enable no-till farming, and eliminate a manure lagoon, you are solving a tremendous number of greenhouse gas impacts and nutrient pollution impacts from large-scale agriculture. So think about what a good story that will be when you can drink milk and sequester carbon. That's going to be a fun story.
What does the go-to-market and sales process look like with these dairy farms today? What are they asking for? How are they looking to change their practices or not? Where are you having to do education versus where are you having to support their existing needs for whether it's creating lower carbon milk or reducing the amount of environmental waste that they generate?
Absolutely. It's a phenomenal question. So the dairy farmers that I've worked with numerous dairy farmers in all over the Midwest and the Southwest and California and Florida, up in New York. I mean, all across the country, dairy farmers. And I've noticed that there's two things that these dairy farmers truly are at heart. They're customer focused. And when I say customer focused, it means the final consumer. And they are environmentalists. They genuinely care about the environment. I think they recognize that there have been practices in the past in the agricultural community that have not been productive for the environment. And they see those and they say, wow, that was bad. How can we do better today? The other thing is they're all capitalists. So if I can offer a solution to them that's financially better than what they're doing today, they'll switch. Currently, that manure lagoon and the application of those nutrients costs a tremendous amount of money for a dairy farmer. That is a very big cost center for the dairy farmer. If I can step in and provide the product as a service, which is why we work with Generate Capital. Generate Capital allows us to build installations of our technology and offer our system as a service to a dairy farmer. We process their manure for them for a very marginal fee, potentially. And then what happens is that we give them back clean water, and then we sell the nutrients, the fertilizer or both fertilizer products. That allows us to get a return on it, solve their problem, and solve an environmental problem as well. The other thing is it allows the dairy farmers to tell their milk co-ops and their final consumers that they're more environmentally sustainable. This is really a huge thing that the consumer, the end consumer, really cares about environmental sustainability of various products.
Hey everyone, I'm Yin, a partner at MCJ Collective, here to take a quick minute to tell you about our MCJ membership community, which was born out of a collective thirst for peer-to-peer learning and doing that goes beyond just listening to the podcast. We started in 2019 and have grown to thousands of members globally. Each week, we're inspired by people who join with different backgrounds and points of view. What we all share is a deep curiosity to learn and a bias to action around ways to accelerate solutions to climate change. Some awesome initiatives have come out of the community. A number of founding teams have met, several nonprofits have been established, and a bunch of hiring has been done. Many early-stage investments have been made, as well as ongoing events and programming, like monthly Women in Climate meetups, idea jam sessions for early-stage founders, climate book club, art workshops, and more. Whether you've been in the climate space for a while or just embarking on your journey, having a community to support you is important. If you want to learn more, head over to mcjcollective.com and click on the Members tab at the top. Thanks, and enjoy the rest of the show.
So if I understood it correctly, you work with Generate Capital. They're helping to fund the infrastructure and the build out of a Sedron system on a dairy farm. The dairy farmers then, instead of having to put their solid waste into a lagoon and then presumably have to pay to transport it out to future buyers of that waste for use as fertilizer, instead, they are or are not still paying you a tipping fee to process the waste and then ultimately purchasing it back from you as pure, cleaner fertilizer and clean water?
It depends upon the location. So currently a dairy farmer, depending on where they are going to spend between, say, 1 and 3 cents per gallon, depending upon where they are and a bunch of factors, to pump their manure into a lagoon and then pump it onto the fields. We step in and we say, in some instances, there'll be no cost to the farmer because their manure looks a certain way, it's in a perfect spot. We may charge between 0 and 1 cent for the application. So they're going to save between 2 and 3 cents, potentially, or between 1 and 2 cents or 1 and 3 cents on the application of their manure just by using us on day one. The products we make are organic fertilizers. What we do is we generally will sell them to organic growers that have a need for these products. The dairy farmer oftentimes doesn't need the fertilizer in these products, or if they do, they can buy it somewhere else for very inexpensive because they don't need a specialty organic fertilizer like what we're producing. So there's a certain arbitrage that's being done on the values of these fertilizers. The dairy farmer on day one, I'll answer it this way. The dairy farmer, when using our technology on day one, has lower costs, lower environmental footprint, and longevity of their farm because they know that there's no environmental action going to be taken on them by a regulator. So they solve three major issues.
As I understand the dairy industry, you've got what I think of as a brand of milk I would buy at the store. Those are actually, for the most part, marketing co-ops. The farms themselves are often independently owned or owned by, the marketing co-op may own some of these farms, but for the most part, the farms are making relatively independent decisions on things they want, though the marketing co-ops may start putting requirements on them around emissions or around environmental regulation. Are you finding your pathway in is through the individual farms, or is it through these sort of larger dairy co-op brands? What does that look like? Because it seems like a challenging sale that you all have had to figure out how to navigate in the last couple of years.
Yeah, absolutely. So you'll see that my understanding, I'm not a dairy farmer, nor am I a co-op owner. So I'll show you my understanding of it. The co-ops are actually owned by the dairy farmers. So that's a huge distinction. So the co-op is going to do what the dairy farmers want, but the co-op is also going to tell the dairy farmer what the consumer wants. And the dairy farmers are very, very shrewd businessmen who understand that a consumer is really, their needs are paramount. The dairy farmers, really, our introductions to them have been dairy farmer to dairy farmer. They're generally family-owned farms, very well-run businesses. Think about it. These are very large businesses that have all the problems of a big business and all the problems of a zoo. They're a very sophisticated entity to run. These are great business owners that run them and are very excited to solve financial problems and environmental problems in one fell swoop, which is a little bit of our mantra. Because if you can make money off of solving the environment, solving environmental problems. If you can make money from solving environmental problems, everyone will solve those environmental problems. If it pays to be an environmentalist, everyone will be an environmentalist. So we've structured everything. We don't rely on government incentives. We don't rely on some sort of tax subsidy. We are structured as a business to operate on first principles from an economic standpoint so that we can solve all these environmental problems without government intervention.
Yep. A market-led theory of change feels like the way this moves from experimental to mainstream adoption as a 21st century pathway in terms of just building solutions that can handle a world that has up to 10 billion people on it, frankly.
Exactly.
So Stanley, let's go from there into some of the origins of the company. You all, not Sedron, but the parent company of Janicki, as I understand it, was actually in the aerospace world and had done some experimental work that the Bill and Melinda Gates Foundation decided they wanted to help further fund. And so maybe walk us through that origin story, which I think is quite fascinating.
Yeah, absolutely. So my father, Peter Janicki, and my mom, Susan Janicki, founded an aerospace company, Janicki Industries, in the early 1990s. That company has grown to be a phenomenal commercial and defense aerospace company. They work with Boeing, Lockheed, Northrop, Airbus, basically everyone you can imagine in the aerospace world, doing large-scale tooling, parts, assemblies, basically aerospace work, and do a tremendous amount of custom engineering. It's very common that an aerospace company will go to us and say, help us develop XYZ. We can develop technologies for aerospace companies. The Bill and Melinda Gates Foundation saw that and said, well, if you can develop XYZ technology for an aerospace company, why can't I ask you to take that out of the box thinking, those engineers that you have, and apply them to developing sanitation technologies? And again, because you're coming from an entirely different industry, you're going to come at it from a completely different paradigm than those entrenched in the existing industry. So that's how we got into it. The foundation said, we will help you work on this. Here's some problems we want to solve. So we worked a lot with them and co-developed omniprocessor with the Bill and Melinda Gates Foundation. There's some wonderful videos of Bill Gates drinking the poop water. I don't know if you've seen that. It's a great video.
I have. We'll make sure to put those in the show notes. It's fantastic.
Phenomenal video. Everyone, great things to say about the foundation. They really, that technology, the business case for it, because it's around selling electricity, really works best in developing countries where electricity prices are high. But we realized that there are some insane market inefficiencies in the United States and other developed countries where that market inefficiency is also causing an environmental inefficiency, causing impact to the environment.
The idea basically is to use biosolids as an electricity source and created a whole closed loop system that is able to take the tipping fee of the biosolid coming in, run it through your process, ultimately generate electricity, generate clean water, and then presumably you have this bio waste that's ash that can be then used also as fertilizer, I presume. Was that the original sort of use case of the technology?
Yeah, that was the omniprocessor. That was the goal with the omniprocessor. And again, because your electricity rates are so high in these developing countries, that business model worked very well. It's very difficult to compete with Hoover Dam or Grand Coulee Dam here in the US. I mean, our electricity prices are so low that that business model didn't particularly work. I will also say the problem, that is less of a problem in the US than slurry waste streams, which is why we said, oh, wow, this Varcor can really be applicable to dairy streams, applicable to this wide range of heterogeneous waste streams, even more so than the omniprocessor.
Because the omniprocessor was taking solid waste in, whereas with Varcor, you're starting with liquid waste, which is more challenging because you have to do the separation to begin with.
Exactly. We also have very high concentrations of things like ammonia, which are very difficult to remove. And that's sort of the magic, is our ability to remove that ammonia from the water. And not only remove it, but recover it and concentrate it and displace the production of fossil fuel derived fertilizers. That's an exciting story.
Going from what you learned with the original Janicki omniprocessor to saying, hey, here's a use case that works in the US, what did that transition look like?
As you can imagine, when Bill Gates posts on his YouTube a video of your company and drinks poop water, lots of people contact you. Lots of people contact you. We got thousands of inquiries from thousands of different types of people. So we were introduced in a crash course, if you will, on waste across the entire world. And a theme that popped up numerous times was agricultural waste streams, such as dairy waste, and the fact that there's no viable method to deal with them in areas, some really major places that have issues. Wisconsin, for example, it rains a lot, and you're next to Great Lakes. You are going to get runoff. Puget Sound region. There's dairies here in the Puget Sound region north of Seattle that they're right on the water. It's very difficult. So we're like, wow, this nutrient pollution issue, there's some real issues here. So we started talking to people and we realized that we needed a technology that could take in a slurry waste stream because there were so many applicable uses of it. So we started working with some of the larger, more influential dairy farmers that really educated us on what is the dairy industry and also their passion for solving these environmental problems. We said, wow, if we could take a technology and really make a dairy farm not have a lagoon anymore, not have land application of dairy liquid, and go to no-till farming, you could solve their problems. So we began the process of developing the Varcor. And we partnered with some dairy farmers who really could lead us along that journey. And then as we developed that, we matured the biosolids industry and the stillage industry as well.
And where is the company today from a commercialization standpoint? And also just how have you financed this? You emerged out of this aerospace R&D company and now are creating a totally new business line. What's been the process of capitalizing the business as you go into commercialization?
Yeah, absolutely. So it's been hard, very hard. I will say that. We're over 200 employees now. We've grown the company. We have installations in Wisconsin and in
Sedron, not Janicki.
Sedron alone. Sedron is a standalone company with different shareholders than Janicki Industries. Over 200 employees, and we've invested over $290 million to date in developing the technology. And of course, from a financial standpoint, that's come from a range of places. It's been obviously project finance from Generate Capital and in building installations. It's been there are several large family offices that invested $52.5 million this year in the company. And of course, previous founder investment by my father. And then some of the dairy farmers invested early on in the process. So it's been a wonderful journey developing the company, raising all of that capital. And in the midst of a banking crisis this year was less than exciting. But I will tell you, it has been a wonderful journey. I can't say enough good things about all of our partners, all the people that have worked with us at Sedron, all the employees at Sedron, right? I mean, people have done incredible things to develop this technology. And I'm very proud of all the employees that we have here at Sedron. All 200 of them, 202, I guess now.
What's next? Like, what do you envision the next 3 to 5 years looking like? This company's not that old, right? I think it was founded in 2017, give or take.
2014 was the original founding of the company. We really started developing the Varcor in earnest in 2018. So there's been tremendous trajectory on growing this company. I will say, where does this company go? We've talked about a few things. We've not even talked about the ancillary impacts. The fact that producing a concentrated organic nitrogen fertilizer is going to reduce the cost of organic crops, which is going to provide equitable access to much more people to have high quality organic nutrients. There's all sorts of ancillary benefits. But if you take that vision that we are going to take waste products and upcycle them into viable commodities that displace fossil fuel derived commodities, my goal as a company is to build out a tremendous nationwide and international network of installations, upcycling these products and displacing fossil fuel derived products, whether that's in the dairy industry. There's no reason that once we get this at scale and are running, there's no reason that the dairy industry couldn't become net zero from a carbon standpoint. There's no reason that we have to have 3% of worldwide greenhouse gas emissions producing ammonia. We can take all of the ammonia and displace that, reduce that industry. Also, ammonia fuel was in the cover of the Wall Street Journal today. The next step is to take ammonia and make it as a low carbon fuel. If you had a low carbon, a found nitrogen that you recovered from the environment, that's wonderful. And then, of course, the whole wastewater industry. The fact that we're getting algae blooms in Florida, in the Chesapeake Bay, the fact that nutrient pollution is such a problem. Capture those nutrients before they go into those waterways. Use them as fertilizer in a concentrated, efficient manner. I see a world where the environmental issues we're seeing in wastewater, in fertilizer, in agriculture, we can play a demonstrable part in solving all of that. And again, in a way that's financially and environmentally sustainable.
And Stanley, if you could wave a magic wand and accelerate that, what would you have that wand do?
That's a phenomenal question. I think I ask that every day. I will say that the ability for people to recognize that we're to that next level as a company. It's not an idea. It's not a pilot anymore. We are building out $100 million installations of this technology on a regular basis. We are growing and building this company. And it's not a risk anymore. So often when I show this to wastewater treatment plant operators or legislators, or they're like, is this risk? This is new, so there must be risk. But we're past that point. I want people to know that if you are a fiduciary for a city and you want to work with Sedron, you're not going to get burned because the technology works very well. We have installations. I'll also say access to capital markets. I would like capital markets to open up a little bit, but it doesn't everybody.
Stanley, this has been a really eye-opening conversation for me. I've learned a ton. Anything we should have talked about or covered that we haven't gone into?
No, I think that we covered a lot here. I'm really honored to be able to talk on your show, and you had phenomenal questions here. It's been a great conversation. I feel like there's so much that we can do on a climate journey, right? As people grow and people learn. And I know my personal climate journey, right? Coming from undergrad in computer engineering, working for software, and now here I am helping run a technology company that every day we're focused on solving climate problems. That's something where someone who can run a podcast such as you do, I think is very cool. And I'm very honored to be on here. So thank you.
Well, I appreciate you joining us and educating us and clearly showing the size and scale of the problem at hand that you are working to solve.
Yeah, absolutely. I'll give you a couple numbers as we close out here. There's over 14,000 wastewater treatment plants in the United States. There's over 9 million dairy cows. There is no reason that the waste coming out of, and again, waste with quotation marks, from every one of those places couldn't be used to displace fossil fuel derived fertilizers. That is closing the loop.
Thanks, Stanley. I appreciate you. Actually, before I close out, let me back that up. You've mentioned fossil fuel derived fertilizers a few times. Describe how the Haber-Bosch method leverages fossil fuels in its current processes.
Yeah, so the Haber-Bosch process was developed pre-World War I to produce and synthesize nitrogen fertilizer. Prior to that, the only source of nitrogen fertilizer was various animal or human waste streams. And what this does is it takes natural gas and you cool it cryogenically with nitrogen from the environment. And then with an oxidant, you're able to combust that and produce NH3 molecule. 50% of life on Earth today, human life that is, would not be alive without the creation of the Haber-Bosch process. This was critical. It is critical in supporting life today. The problem, though, is it's critical, but at a cost.
Just in terms of the ability to feed the planet, feed the human population of the planet, I guess, specifically.
Exactly. 50% of the human population would starve to death without the Haber-Bosch process. but again, at a tremendous cost, and also both from a societal cost with environmental cost, right? 3% of worldwide greenhouse gas emissions. It also has put countries like Russia's 25% of the world production of ammonia. These are potentially bad actors that are in a spot that wield tremendous power on the world stage from a food security standpoint. Whereas if you could produce something where each country could recycle its own nutrients effectively and efficaciously, you'd be in a spot where you wouldn't have petrochemical states managing that. You could have local economies being able to do that.
That's a great note to end on, and thanks for explaining some of the broader context with us as well. Stanley, thanks for your time.
Of course. Thank you so much, Cody. We'll talk soon. Bye.
Thanks again for joining us on the My Climate Journey podcast.
At MCJ Collective, we're all about powering collective innovation for climate solutions by breaking down silos and unleashing problem-solving capacity.
If you'd like to learn more about MCJ Collective, visit us at mcjcollective.com. And if you have a guest suggestion, let us know that via Twitter at MCJPod.
For weekly climate op-eds, jobs, community events, and investment announcements from our MCJ venture funds, be sure to subscribe to our newsletter on our website.
Thanks, and see you next episode.